Hi, I just want to make a quick update on a video that I uh, previously uploaded. It was a bigger video, but for a number of reasons, I had to cut off a piece of it in which I explained some results that I've managed to discover within my research. And I was generally unsatisfied with the final result. So I'm making this update based on a new paper that I'm trying to get published on sort of like traditional journals. More of that on another video. But anyway, I just want to frame basically what I'm trying to say with this new paper, which is rather simple. Let's start first with something from general relativity. You might have heard about the three so-called classical tests of general relativity, which were thought of by Einstein, and I've written them down on this blackboard over here. They are supposed to be, this first one here is the so-called gravitational redshift, which has been famously tested by the Pound experiment in the 1960s. Next, we have the so-called perihelion precession or upside-down precession anomaly. And there's just a little bit of a caveat here. The formula that you see here on the blackboard is the result for, in terms of arc seconds per revolution. When you hear about people talking about Mercury, you hear the result quoted in arc seconds per century. So to convert this, you gotta know, in the case of Mercury, how many orbits does it make per century. So the number is a little over 400, something like that. So you take the number 400 something and you multiply by this and you get the 43 arc seconds per century that people quote for Mercury. Next, and last but not least, we have the so-called bending or deflection of a light beam. So if you're thinking in terms of light that's just grazing the surface of the sun, when you put the appropriate values here, you get a result that is about 1.7 arc second, something like that. Tiny little effects, all of this. And by the way, don't worry about the notation, which is what do you mean by alpha and what do you mean by B0 and B0 and so on. It doesn't matter. The only thing that we need to worry about here is that besides this being a thing that you can calculate within general relativity, which is the mainstream view, what we need to pay attention here are these three factors that you can see over here. 2 minus beta plus 2 gamma over 3 and 1 plus gamma divided by 2, which depend, of course, on this beta and this gamma parameters, which are dimensionless numbers. What are these? These are what's known as the Eddington-Robertson-Schiff, or ERS parameters. And they are part of a larger set of parameters, which composes what is known as the parameterized post-Newtonian formalism, or PPN formalism, which is about 9 or 10 parameters total. But we don't need to worry about the others. Only these are the important ones for these particular tests. And what do they mean? Why do we need them? Well, you take some model of what you think is going on in, say, the solar system. In the case of jar, that would be the Schwarzschild solution. So it's not really quite the Schwarzschild solution, but for sake of brevity, let's just call that. You can read a little bit more on that same paper that I have linked in the description. So when you substitute that solution, you make the calculations and so on, you can find this in practically any textbook of general relativity. You come up with the results for these numbers, or in other words, they are model-dependent numbers. So here you have it. Beta and gamma are simply one. It's quite simple, in fact. And to state what they are. So if you sub these values here, that's why you get agreement with the observation, because this factor goes to 1, and this factor goes to 1. So you get exactly what is observed according to GR. Well, so far so good. I just talk about mainstream stuff. But what does my research has to do with any of this? What does it bring to the table? Well, I have this framework, right? Which I'm not going to explain here in any detail because it involves a substantial amount of differential geometry. If you want to read about that, like I said, you can check out the paper linked in the description. But the important thing is that I got a particular model, which I fed to the machinery of the formalism. And this model, from this model, I managed to extract these predictions and put it on this form. What model is that? Well, it's quite a very simple model, in fact. I call it Newton in quotes because, well, you basically have a single component, which kind of like goes as the inverse of the distance from the origin. And this is not quite the same as a Newtonian potential. The mathematics are a bit different, but still the physics is exactly the same. For one thing, you get an inverse square law as you would expect from Newtonian theory. And really what this is modeling is simply you have a massive point particle, right? And we want to simply make the simplest explanation of the gravitational field surrounding this little point. And this is pretty much the same as you get in the usual Newtonian theories, hence the quotes, the Newton in scare quotes, because the scare quotes is because the math is not the same, quite the same. But anyway, you can, in this paper, I show that you can calculate these effects from general relativity and you can put it in this form. However, there's a difference. And where's the difference? They lie precisely on the ERS parameters. After you've done the calculations, you can, I show there in the paper that you end up with a value of theta, same thing as GR, unit. But for gamma, you get 0. And that means that if you substitute this over here, you get different results from what is observed. Now, at this point, you might wonder and think to yourself that this is really bad. But actually, it's not as bad as that, because a few things to keep in mind. The first one is that this PPN business was invented to compare GR with other so-called metric theories. What's a metric theory? Well, in a nutshell, it's kind of like this. You basically start with GR as your foundation, and then you put stuff on top of it and make it more complicated. And once you do that, your equivalent of the Schwarzschild solution will yield different parameters. So in the end, you get different predictions from GR. So that's how you can compare these different theories. So why am I mentioning that? Well, because my theory is not an example of a so-called metric theory. And from that alone, it's really surprising that I'm able to show, to compute, that these particular predictions can be cast in exactly the same form. So this is rather unexpected. So much so that as early as like a year ago, or perhaps even less than that, I wasn't really expecting this to be true for the Newtonian case. But I came to see that this is indeed, in fact, what happens. And this is suggestive that we are going the right way here. We haven't reached that quite yet. Because like I mentioned, this is the Newton in square quotes. This is just one model that the theory allows. It allows other models. This is for the vacuum in particular. But I found a number of other solutions already. The thing is, none of the solutions that I found are able to give me a gamma of unity. Because if they did, I would no doubt put that on the paper already, right? But you should keep in mind, just because I haven't been able to find a fix to this discrepancy doesn't mean that there is none. It just means that I haven't found it yet. It's not a proof that there is none. That would be an argument from silence. Speaking of, we can also think of this in physical terms, because remember the name of the formalism is called PPN, for post-Newtonian, and we're dealing with the Newtonian regime here. So, from physics alone, if you're dealing with a post-Newtonian effect, it stands to reason that we wouldn't be able to get that effect from a purely Newtonian case. So it makes sense here. Although this is not what happens with GR, because in GR, it turns out that you can separate the Newtonian from the post-Newtonian regime. It all comes in one bundle. But here, that seems to be not the case, which is different. But again, just because it's different doesn't mean that it's wrong. Doesn't mean that there is no adequate post-Newtonian formulation here. Finally, as a third point, you'll notice that even in this Newtonian regime, we are able to get the beta right. And this is very interesting because it suggests that the post-Newtonian regime in our scheme, in our theory, is regulated or governed not by two ERS parameters, as is the case with GR, but just one. And that in turn suggests that our theory, if correct, is actually simpler than general relativity, which makes it more attractive, if it's the case. I must stress that part. And if that's true, it also has some implications in terms of the interpretation of these parameters. Let me show here. Let me show here. Let me show you real quick a review by Clifford Will, sort of like a legend in experimental GR. He here you can see the full table of the PPN values, and he explains what they are supposed to mean within the context of general relativity. So here you see, the gamma parameter is supposed to mean how much space curvature produced by unit brass mass. So the interpretation here would be different because of the differential geometry that I mentioned. But for beta, it's supposed to be how much nonlinearity, quote unquote, in the superposition law for gravity. Now, this is interesting because my field equations are not nonlinear. They are in fact linear, just like it's the case with the Maxwell theory of electrodynamics. So it's very interesting because although there's this nonlinearity thing going on for GR, because GR uses nonlinear field equations, that's not the case here, because I've already got that covered with the Newtonian case. And that in turn suggests that the interpretations will be different, even though the numerical values are are supposed to be pretty much the same. Which again is an interesting point for us to discuss. But anyway, that's all I wanted to say. I will um, try to edit this and shorten a little bit further. And I'm going to prepare a new video explaining this paper and the difficulties in getting published and what happened to me thus far, little report on my activities on this matter, and so on. So for you to have sat through this and watched through the end, thank you for watching, and hopefully I'll see you later. So bye-bye.